Good afternoon, everyone. This is Dan Broderick here with Psylotech, and I'm here with my colleague Chuck Spellman. We want to be respectful of your guys' time this afternoon, so we're going to try to limit our discussion to about 30 minutes, 35 minutes or so. We will have a section at the end for questions, so there's a couple different ways. You can type in your questions in the question box, or you can also raise your hand, and I'll be sure to open it up to you at the end, and you can speak your question out loud. But for now, I'm going to pass it over to Chuck. Chuck's been with Psylotech for about 10 years now, and 8 of which he's been developing this product and working with it, and I think he's really excited to talk to you all.
Hey everyone, thanks Dan for the gracious intro. As Dan mentioned, today we're going to take a look at the under-microscope load frame we've been developing here for the past few years and kind of some new developments, but also go over a quick application note in a specific area just to show you some of the possibilities and the key features of the load frame itself. And as Dan mentioned, feel free to put questions in the chat window there. Okay, so we'll get started here. So we were approached by an large automotive company not too long ago, and they were trying to figure out better ways to simulate the bond between the frame and the different frame components. So a fracture mechanics model was needed to simulate those well. We ended up looking into cohesive zone models, which have been around since the 60s. They're pretty well developed in the literature, so we decided to go down that route. And an addition that we wanted to add to it was time and temperature dependencies of these fracture mechanics. So that's kind of where the work is going. So in the cohesive zone models, what we have is, if you're not familiar, we're obviously measuring the stress, the load of the specimen, but then also this displacement here, the crack tip, the propagation, and we measure the gap here as the crack tip moves. So there's a few different ways to measure this, and we'll go over those in the next few slides. But these methods are very useful for getting the properties of failure, and specifically this is an adhesive joint between two pieces of metal. And we're building off of work here with some colleagues of ours, Professor Ken Lichty at University of Texas, but also his co-authors here. So in order to perform these experiments properly, we first needed to make some specimens that were pretty repeatable and very constant. So what we did was we sandwiched 2 pieces of steel. We sandwiched between an adhesive joint, and we used a razor blade to initiate a crack, cycled those specimens until the crack started growing, and then we imaged at a high rate once that crack started growing all the way until failure, ramped until failure. So I mentioned there's a few different ways to measure the crack tip. We call it crack tip opening gauge. 3 of the methods that we can use with our load frame include compliance monitoring of the displacement, loss of DIC correlation at the crack tip. You'll often see errors in DIC, and this is actually a method used, and it's been published. We didn't use that in this particular study here, but what we used was DIC displacement on both sides of the crack. So we had 2 regions on either side that we were able to look at to get a full field displacement or just a single number for each of these sides. Now, so coming into the first kind of key benefit of the load frame in performing these experiments was what happens with high magnification DIC, and you can see right here we would have our, let me get my pen out, we would have the objective comes in here from the top, and you can imagine this images the specimen which would be placed right here, or sorry, more in the center here. Now if this specimen moves out of plane, it can cause issues, especially with these high resolution 2D optics we have. And so to combat that, we've designed this load frame all along an axis here. You can see the actuator, the crosshead, the displacement sensor, the load cell, and all the support structures along the same plane. Now we contrast this to, in our first design here, you can see we weren't so knowledgeable about the optics and the issues that can come up. So you'll see that this is a lot of the designs of a lot of other competitive frames that are out there use a motor that's attached to some sort of a gearbox and dual lead screws, dual opposing lead screws. And that causes issues with out-of-plane motion. So we weren't able to get high magnification 2D DIC. So that was kind of one of the first key benefit of this new load frame, is that we were able to really eliminate those errors. And what we ended up with was displacements that were all within the 50x objective limit of our focal plane. So this high magnification allows us to see things that were not possible to be seen with other tools. Specifically in the paper that we reference here, they use a large-scale MTS or Instron type load frame with just a tripod-based camera. So minimizing the out-of-plane motion allows us to get high-resolution DIC data. And the centering stage, which we actually put under the load frame, allows you to center any specific or any arbitrary point along your specimen, whether it be the center, the side, or the extreme edge. And that's actually more, you see a lot of other load frames that have dual moving crossheads. You can center only the center of the specimen, but with our secondary X stage, which travels below it, you're able to center any arbitrary point, including bending specimens. So the next key reason we leverage our load frame for this particular test was that our high-resolution sensors are able to see a lot more than any other competitive system. So using a capacitive voltage divider as a load cell, we're able to get about 100x more resolution versus a typical strain gauge load cell. So that gets us around 8 millinewtons of resolution plus noise plus accuracy on a 1600 newton sensor. So typically you'd only see a fraction of that, much worse resolution on a strain gauge load cell if you have a 1600 newton range. So you can imagine it being like having a 16 newton load cell and a 1600 newton load cell simultaneously on the load frame. So it's a very highly sensitive device, but it's also temperature compensated for drift in case there's any temperature fluctuations in the lab or in the room that the frame is housed in. Our displacement sensor is actually mounted right here, and for DIC you're getting the ideal local displacement fields of your specimen, but sometimes you need more of a global displacement, and instead of using the encoder reading, which is what a lot of other companies will do, we actually have this displacement sensor directly mounted to the crosshead here. So we get an exact reading of the crosshead, which we can control off of. So we don't use DIC in the real-time control loop due to its problematic loss of correlation. You can kind of have the sample break if you were to lose correlation. So with an 8 millimeter stroke, we're able to get down to a 40 nanometer resolution displacement reading using these inductive coils that are housed. You can see this is just this turned on its side, housed inside of our displacement sensor. Not a requirement for doing under microscope DIC, but it does help for some of the more advanced control features. And you can see here we use this sensor to measure the compliance. So this range can be quite small compared to, say, the total range of this test in strain. But we're able to see these hysteresis loops to very small changes and note when exactly that crack tip is opening by looking at the hysteresis loops. Now, the final kind of key benefit that our load frame offers here is its modularity and its ability to allow the user to have a very repeatable test and statistically get enough data from different samples to really know if there's an improvement in the bonding method and to get enough data for the fracture mechanic parameters. So that primarily in this test came about because of these specimen grips we have called Arcan. They've been in literature for few decades now, but they're a pretty interesting structure. And what you do is with the same specimen geometry, you see it's a butterfly here clamped between the two halves of metal. You're able to do multimodal, but also just unimodal testing, so mixed mode here, tension here, and shear, pure shear here. So it's the same specimen, but you're able to eliminate the geometry effects that could be coming up, and all you have is the material properties. So we squeegeed those with the epoxy, and we're able to get pretty uniform specimens that were all clamped very similarly. Another feature of the load frame that allows for really kind of easy, just no mess data acquisition and data processing is the fact that we have a trigger output for imaging. This is a BNC 5-volt trigger, and it can trigger an image, it can trigger another controller. It's really very flexible, and what it does is it allows the load channel or any other channels that are coming in on our load frame to be synced up in time with an image. And you'll get that as an output in the file. It's a plain text output with a trigger number for each point that it has a trigger associated with it. What you can also do is use the DC output of our sensors to get another acquisition system involved, but we find that this is an easier way to set it up. Speaking of the software and the flexibility it has, we actually written it all in LabVIEW, which is a pretty comfortable environment for most scientists from what we've heard. And it's open source, so if there's any modification that needs to be made for a particular auxiliary controller or any sort of a new device that you need to add that we don't have that we don't offer, it's something that you can add in. We have pretty high flexibility of different segments to run, sine wave, square wave, and also each segment within your test can have a digital filter that's added at a different frequency, actually. So you can imagine ramping up slowly, having a pretty low filter, but then wanting to see a fracture event at a certain time that you expect. You can turn down the filter and see really high bandwidth, up to 5 kilohertz output data. So just do a quick recap of those experiments. The load frame allowed us to do high magnification DIC. The load cell allowed us to get a high resolution stress reading, and also aided in potential compliance monitoring, although we didn't do it in this case. We performed this test on numerous samples very easily and very repeatably by just dropping in the specimen into the Arcan grips. And a few other features that we mentioned that didn't quite come up in this example, but the open source software, high-speed actuator, temperature controller, which is actually something we're just launching in Q4 of this year. So we just actually shipped the first one not too long ago. And then all of our different grip fixtures that we offer, in addition to the fact that our grip interface is completely open and allows anyone to make their own grips if they decide to. So this is one of the key benefits of the load frame that didn't get to in this experiment, didn't really come up, but the load frame is based on a direct drive motor actuated ball screw. So this is the motor, kind of a cross-section view. These are the magnets, and then, or sorry, the windings. The magnets are here directly onto a ball nut. So most other load frames use, first of all, lead screws, which are a lot less efficient and have more play. But we use a ball screw, so it gives us a lot of speed and efficiency for high load, and get this whole actuator very compactly into this space. So it saves us space. We can fit into small microscope chambers, but it also gives us a lot of speed and force capacity. So depending on the configurations, it could be up to 1 meter per second. You lose some load capacity there, but very fast. And we can actually handle fatigue loading depending on the load and the number of cycles. You get the amplitude of that frequency that you'd be able to run. So just a quick note about who we are. So the company was founded in 2006 by Dr. Alex Arzmanidis, and we have a mission to to enable product designers to really make their job more efficient. So in the MUTS, it comes in by early R&D and providing data for R&D experts who are going to then pass along information or better materials to their product designers. But we also have another business line, which is called Visca. It's a nonlinear viscoelastic model, a polymer model for really getting really accurate data and reducing the iterations needed for designing products with simulation. We're based just north of Chicago in Evanston, and our parts are made, we're assembled, calibrated, tested, and machined in the US, so it's all local manufacturing. And you see here's Dan Broderick right here, my man, and here's Alex on the right here. It's good-looking guys. So with our offering here, we're trying to do is make your job easier, help you accelerate either the R&D or product development phase, and we try to do that with only having very minimal needs from us in the long run. So the actuator only has one wear item. We're made here, we're supported here, we can be out very quickly to help support a system. We provide training, very detailed manual, and drawings of all parts, relevant parts. And each load frame is uniquely crafted, and if there's something that we don't have today, it's something that we'd like to talk about. You know, if it's a feature that you need or a different grip modification, there's tons of different modifications that can be made to these systems, and we'd love to help you make it fit for your work. So a small selection of some of our current users in the field. These are more the publicly known ones. So ARL, we developed the first system. We leveraged an SBIR grant with the ARL, the Army Research Lab, for their body armor soldier protection services arm. So they have a very unique frame, but it's evolved into the MUTS. It's a very similar platform, and they've been publishing a lot of data on it recently, and it seems to be working out very well for them, but so well that these other companies have ended up, or other universities have ended up joining on too. And there's a few other industries that we're also in, several large companies that have our frames. So that's what I have for you today. We'd love to have some questions come in. If anything comes up that we're not able to get to, please don't hesitate to contact Dan. His information is here on the right. And yeah, thanks for the time.
Thanks, Chuck. We actually have a couple questions here, so we'll start in the order they were received. The first one is there smaller than 1.6 kilonewton load cell for the load frame, and does the use of the smaller load cell increase resolution better than 8 millinewtons?
Yeah, that's a good question. So the load cell, the base load cell, so the capacity of the smaller system, of the 1.6 kilonewton, it's meant to go up to that load capacity. So the actuator would always be about up to that size. However, we can swap in any load cell we want. We offer also a 100 Newton load cell that is a microscoping load cell. So we call our sensor technology a windowing or microscoping load cell, and that's also a capacitive voltage divider that would get you about 100 times better than a 100 Newton strain gauge load cell. So imagine a 1 Newton strain gauge load cell and a 100 Newton strain gauge load cell. Now that's about as low as we're comfortable going, just because of the internal structures of load cells. As you decrease in load capacity, you get higher resonance. But there are some off-the-shelf load cells that'll go a little bit lower than that. I've seen a few from different companies, and what we can also do is outfit the system with any other load cell or strain gauge load cell off the shelf that may fit your needs more. But yes, we do have a 100 Newton load cell, and it would scale down in resolution to be better than the 1.6 kilonewton.
Great, thanks, Chuck. The next question is, do you sell this equipment in Europe?
So we do offer the systems in Europe. We don't currently have a distributor set up in Europe, but we do we can support the systems from here, assuming that you're happy to wait maybe an extra day or 24 hours for a reply in the communications. But we do service Europe.
Great. And then, is this system SEM compatible?
Yeah, no, thanks for asking. I'd like to show all the different possibilities. Now, of course, every SEM looks a little different. The system it's really suited for optical use. It looks like this slide ran off a little on me here on the bottom. I apologize for that. We find that optical case for DIC is you get about 80% of the benefit and a lot less of effort in setting up the test. So we recommend optical, but the system can be vacuum rated, and we have a specific system that is, let's see if I can find it here. So this system is actually a vacuum rated 5 kilonewton system that's shortened a little bit compared to the standard actuator. You can see here it's a little bit short. These three images are about to scale. And this actuator is vacuum rated with a different kind of encoder on the front, you can see here. But it weighs a little bit less, it's a little bit smaller, and it's meant for the SEM. It doesn't fit the smallest of SEM chambers, but it is designed to accommodate medium to large chambers, and it just performs just the same as the other three frames.
The next question is regarding the grips. They were curious if they can manufacture their own grips.
Yeah, let me pull up, oops, that's the first one. So here we have a plethora of grips that we offer off the shelf. We do a wedge tension, we call it. It's more of a wraparound grip. We have a clamp tension, which is a pretty modular, a pretty flexible grip. You're capable of clamping just about anything. The bending fixtures that you're probably familiar with, compression platen, and here we have the Arcan. This is the same grip. It's just kind of shown 3 times here to show you the different angles, but this is all in one. One that's not pictured here is the platform grip, which is a platform that has multiple tapped holes that are available for the user to just put in whatever feature they want on top. Say it's a fiber holding mechanism or something that we haven't thought of yet. There's a lot of different applications out there. And we're happy to work with you, and if there's a grip that doesn't exist, make it. But if you'd rather do it in-house and you have the ability to do wire EDM, high precision, high tolerance machining, what we do is we offer the dimensions of this T-slot, and we can definitely get you started and help you out machining any type of system that you'd want to put in between the T-slot. So it's an open platform, and we do have a lot of options that seem to cover most of the market, but of course there are a few things that we don't do, and you're more than welcome to work on those on your own or with us.
All right, the next question is relating back to the first one. Is it easy to swap load cells, or does it have to be done by a service technician?
Yeah, the load cells are actually all this rail. So let me pull up a good picture here. So we have this rail insert here, and you can see that these 3 bolts on each side are all that clamps the load cell on, and then there's a connector on the back, like a D-sub miniature connector that's just not pictured here. And that all you'd have to do is unscrew the connector and pull off the load cell there. Let me see if I find another picture. So you see here, this is the load cell, and it just slides right off of these shafts here. So it's a relatively easy thing to swap out. Now, of course, we designed it such that we don't think you'll have to with most applications, but if you want to put a strain gauge load cell on there, or if you want to have the 100 Newton and the 1600 Newton, there's definitely availability, and there's options, including things as extreme as having, say, a torsion actuator on one side. We could have a 3-axis load cell off the shelf that we worked with another company to make. That could attach to a crosshead here that also has a motor which applies torsion to everything. So you'd have a axial cross-it here, torsion cross-it here with a torsion load cell. There's a lot of different options, and it's the kind of thing that's not hard to be hard to swap out.
All right. And for now, it looks like the last question is it possible to run tests at elevated temperatures? Is there some kind of device for local heating of specimen?
Yeah, I'm glad you asked that because we actually just developed this year and came out this fall with our new temperature chamber. So this chamber goes from about -100 to +200 C. It's in the polymer ranges right now. We do have plans to increase that for potential metal, high temperature metal usage or ceramics. But right now it's a chamber. It goes actually between, this is the 1.6 kilonewton. The chamber is kind of here between the shafts. So it sits within the normal footprint of the actuator aside from the heating cartridge here on the side. It makes the actuator a little bit longer, or the whole load train a little bit longer in total, but no wider or taller. And actually we still are able to fit the microscope into view the specimen here. So it's compatible with DIC, microscopy, and it just fits in with the way the load frame is suited now, allowing all the same sensors. And we actually have machined these grip extensions to minimize any drift that might come in because of the heat and the cool that's in here. So it's a liquid nitrogen cooled cartridge heater heated temperature chamber with 0.5 degree stability, and it's compatible with DIC, which is with high magnification DIC, which is pretty unheard of with this market.
All right. If there's any more questions, feel free, everyone. You can ask them. I think Chuck and I are going to hang out on the line for a few more minutes to see if any more questions come in. But at this point, I would like to thank everyone for joining us. We always welcome any chance to talk about this, and if you guys would like any more information, you can feel free to contact me directly at dbroderick